Imagine the whole planet wrapped in white. Not the casual dusting of a temperate winter, but a hush so complete that even the roar of the sea seems muffled beneath a skin of ice. Picture continents you barely recognize stitched together into a supercontinent called Rodinia, while the sun sits a little less bright than it does today. Now ask the question the rocks keep nudging us toward. What really happened during Snowball Earth? If you like calm science stories, please give this video a gentle like and subscribe. That image, Earth as a slow, spinning snowball, is sensational enough to live in a museum poster, but the truth is subtler and far more interesting. There are mechanisms, feedbacks, and stubborn pieces of geological evidence that, taken together, tell a story of an extraordinary planetary crisis. The story reaches into the chemistry of air and sea, into the slow shuffle of continents, into the stubborn survival of life in the oddest of places. And because the evidence must be read in stone, much of the narrative is detective work, hypotheses, counter-hypotheses, and the occasional clue that could rewrite the scene. Let's begin with the stage dressing. Imagine the planet as it was roughly 700 million years ago, give or take a few tens of millions, in the late Proterozoic eon. That figure, like almost every number in deep time, wears a hat of uncertainty. Radiometric dating gives us ranges, not a digital timestamp. Still, geologists have found glacial deposits in rocks that today sit in tropical latitudes, and those deposits are the first jolt to the imagination. It raises a question that never leaves you. How could glaciers form at the equator? Part of the answer starts with Rodinia, the great supercontinent. When land is gathered together, it changes the way the planet behaves. Large continental masses have more coastline exposed to erosion, they alter ocean currents, and crucially, they change how rock interacts with atmosphere and water. One process in particular, chemical weathering, matters a great deal. Weathering is the slow breakdown of silicate rocks on continents by rain, rivers, and root systems. When silicate minerals weather, they draw carbon dioxide out of the atmosphere and lock it away in dissolved ions that eventually end up as carbonate rocks. Think of weathering as Earth's very patient scrubber for CO2. Now imagine Rodinia rifting apart. Rifting can increase the exposure of fresh rock to weathering. Newly broken surfaces weather quickly. If weathering accelerates over geological timescales, it can reduce atmospheric CO2 enough that greenhouse warming decreases. Remove some of the greenhouse effect and surface temperatures drop. That's one ingredient. Another ingredient is the faintness of the sun. Over the billions of years, the sun's energy output has not been constant. A long time ago, the sun was slightly fainter.
By the Proterozoic, it was closer to its modern brightness, but still not identical. Models indicate solar luminosity then was a few percent lower than today. A few percent might sound small, but in the balance of planetary heat budgets, it matters. Less solar input makes it easier for cooling processes to gain the upper hand. Combine these factors, tectonic reorganization that promotes weathering, a modestly dimmer sun, and possible changes in the biosphere that alter greenhouse gas concentrations, and the climate system can be nudged towards a colder state. But that alone does not explain a global freeze. The crucial actor is a feedback loop so effective it is often dramatized as a runaway, the ice albedo feedback. Albedo is a simple, useful word. It describes how reflective a surface is. Fresh snow and thick sea ice have high albedo. They bounce a large fraction of incoming sunlight back into space. Ocean water and dark rocks have low albedo. They absorb sunlight and warm. If ice spreads from the poles towards lower latitudes, the planet reflects more sunlight overall. More reflection means less warming, which allows more ice to accumulate. In some conditions, that loop feeds on itself. A little cooling begets more cooling, until, in modeled scenarios, ice can march toward the tropics and beyond. That cascade is why scientists use terms like snowball and runaway to describe the possible outcome. There are important nuances. Whether ice can truly cover the entire planet depends on factors like ocean heat transport, atmospheric composition, and the thickness of the ice. Models differ. Some show Earth trapped in a virtually global freeze. Others allow persistent bands of open water at low latitudes, a slush ball Earth. The difference matters for biology and for how the planet eventually warms again. One further twist is a hydrological effect. If ice really does scrub the planet of exposed ocean, evaporation and precipitation patterns change. Weathering, the CO2 sink we mentioned, slows because there's little exposed rock under liquid water in rainfall. That would seem like bad news for freezing, but it is actually part of the escape hatch. Weathering normally removes volcanic CO2 from the air. With weathering curtailed, volcanic gases accumulate. Volcanoes do not stop erupting just because the planet is cold. Over millions of years, the atmosphere could slowly soak up huge amounts of carbon dioxide from volcanic sources. In a nearly sealed, highly reflected state, CO2 accumulates because the normal planetary sinks are starved of reactants. Eventually, the greenhouse effect could rebuild strong enough to overwhelm the albedo effect and trigger a rapid thaw. We've already touched on the big players, Rodinia's configuration, a slightly dimmer sun, weathering, albedo and volcanoes, but there are more subtle contributors and interleavings. For instance, the composition of the atmosphere does more partly involve CO2.
Methane and water vapor are also greenhouse gases, and biological processes influence their concentrations. The ocean's chemistry, especially dissolved oxygen and ion states, shifts when circulation and ice cover change. Some long-term feedbacks, like the burial or release of organic carbon, can nudge the system in one direction or another, sometimes over tens of millions of years. Because the timescales are so vast and the record in rocks is fragmentary, scientists rely on several approaches simultaneously: sedimentary evidence, chemical fingerprints preserved in minerals, and climate models that test how the system responds to different forcings. Each approach brings strengths and caveats. Models can show what is possible given assumed parameters, but their outputs depend sharply on those inputs. Geochemical proxies in rocks record past conditions, but are complicated by local overprints and later geological processes. That is why the phrase, "the rocks hold the answers," is more accurate as, "the rocks hold clues, and we assemble a case from those clues." One of the most gripping clues comes from glacial deposits in places that are today near the equator. Drop stones, large stones that appear in fine-grained sedimentary layers and look as if they were dropped from an iceberg into a calmer sea, have been found in Neo-Proterozoic rocks in regions such as Namibia, Australia, and parts of North America. They suggest that icebergs were present at low latitudes. Alongside drop stones, there are striated bedrocks, grooves etched into bedrock by the passage of glacier ice. Finding such features in rocks that were deposited near the equator forces us to confront a possibility that, minutes before you learned this, might have seemed improbable. There are also chemical signals. Carbon isotopes, for example, record shifts in the global carbon cycle. When the carbon isotope ratio of sedimentary carbonates jumps or dips markedly, it points to changes in the balance between organic carbon burial, weathering inputs, and atmospheric CO2. During the intervals associated with the putative Snowball events, isotope profiles display dramatic excursions that require explanation. And then there are cap carbonates, unusually thick, fine-grained carbonate layers that directly overlie glacial tills in many localities. Cap carbonates are significant because they appear to form rapidly after a deglaciation, in oceans with chemistry very different from the pre-freeze seas. Explaining their origin will be one of the detective arcs we follow in a later chapter. All of this, however, raises immediate questions. Could a fully ice-covered ocean still produce drop stones? Would striations be preserved under kilometers of ice? How do cap carbonates form, and why do they appear in so many separated locations? And critically, how did life survive if the sunlit surface was buried beneath ice? I want to pause here to emphasize an important caution that pervades this whole story.
There are competing models and interpretations, and many of them are reasonable. The Snowball hypothesis, in its strongest form, proposes global ice cover reaching to the equator. The slushball alternative suggests thick ice at high latitudes, but persistent open or thinly iced waters in the tropics. Each model handles the evidence differently. Some argue that simple physical oceanography makes a total freeze unlikely. Others point to the global synchrony of some glacial deposits as evidence for pervasive icing. The scientific community does not yet have a single narrative that satisfies every line of evidence. Rather, we have several plausible narratives, each with strengths and weak points. Throughout, I'll try to maintain that humility. When something is contested, I'll say so and explain why. Let's return to the mechanisms, because the physics is beautiful in its starkness. Picture the planet before the freeze, continents arranged in Rodinia, seas circulating in patterns shaped by that arrangement, sunlight warming lower latitudes more than higher. Now consider a persistent reduction in greenhouse gases or a step change in the distribution of continents that increases weathering. Temperatures fall. Ice forms at higher latitudes and slowly creeps equatorward. Each additional kilometer of ice increases the planet's albedo and reduces the heat absorbed from sunlight. As the reflective surface expands, the balance tips. In many model runs, once ice reaches a certain latitude, the system rapidly cascades toward near-global ice cover. What happens to the oceans then? In a strongly iced planet, the surface ocean could be capped by thick sea ice.
If the ice is thick enough, exchange between the atmosphere and ocean surface becomes severely restricted. Evaporation and precipitation patterns change, the hydrological cycle weakens. The result is something akin to a planetary hibernation. Beneath the ice, however, life in its most tenacious forms could persist. Hydrothermal vents at mid-ocean ridges, warmth and chemical energy, continue to operate regardless of surface conditions. The chemistry at those vents supports chemosynthetic communities that do not rely on sunlight. Elsewhere, thin sea ice or openings called polynias could permit limited photosynthesis in localized spots, and microbial mats and stromatolites, layered microbial communities that can trap and bind sediments, are notorious for their resilience. I said earlier that volcanoes do not stop. That's a crucial point. As weathering wanes under an ice surface, volcanic outgassing can continue to pump carbon dioxide into an atmosphere that has lost one of its principal sinks. Over geological time, volcanic CO2 could build upwards to levels many times higher than pre-freeze concentrations, at least according to some climate model scenarios. How high?
Model estimates vary widely. Some simulations suggest very large accumulations, while others, using different assumptions about atmospheric chemistry and ocean exchange, give lower values. It would be irresponsible to offer a single number as the truth. The qualitative picture, though, is straightforward. With weathering paused, greenhouse gases can accumulate until they reassert control over the climate. When that tipping point is reached, the thaw is not gentle. Models that simulate a rapid deglaciation show intense warming as greenhouse forcing overwhelms the high albedo. Ice sheets melt, sea levels rush back, and massive amounts of meltwater pour across previously frozen landscapes. Those catastrophic meltwater pulses would transport sediments, reshape coastlines, and flush the oceans with nutrients and ions, a sudden geochemical upheaval. The cap carbonates mentioned earlier are one sedimentary signature consistent with such rapid ocean chemistry change: warm, carbonate-saturated waters precipitating carbonate minerals across formerly glaciated shelves. But again, the formation pathways of cap carbonates are an active research topic. They may involve oversaturation caused by CO2-rich waters, rapid shifts in pH and alkalinity, or even biologically mediated precipitation once photosynthetic communities re-establish themselves in thawed waters. The biological consequences of the thaw are where the story grows particularly intriguing. A sudden influx of nutrients from eroded continents could fertilize the oceans, spurring blooms of microbes that, through their metabolic activity, alter oxygen and carbon cycles. There are hypotheses that link these post-glacial nutrient surges and oxygenation events to the subsequent appearance of more complex multicellular life, including the Ediacaran biota and later the Cambrian explosion. Those links are tantalizing and plausible. Biological systems respond to nutrient availability, and oxygen levels constrain the complexity of animal life. But causation is a knotty affair in deep time. The idea that Snowball Earth directly caused the rise of animals is an attractive narrative, yet it must be presented as a hypothesis supported by circumstantial evidence, rather than as a simple chain of cause and effect. Before we return to the rocks and the more forensic aspects of the debate, it helps to consider an analogy for the whole process. Think of Earth as a house with a thermostat, a fireplace, and an open window. Normally, the fireplace, volcanoes, heats the house a little. The thermostat, greenhouse gases, keeps things at equilibrium, and the window, albedo, reflects some sunlight away. If someone opens a new window, increased weathering due to exposed rock, the house cools. If enough windows are opened and the thermostat is turned down, you could get to a point where the house is chilled throughout.
If for millions of years the house remains cold, the occupants adapt in ingenious ways. They huddle by the fireplace. They move into hidden rooms. Then the fireplace is stoked over and over, volcanic CO2, until finally the house warms so rapidly it feels almost oven-like. The occupants spill back into the rooms they had left, and the house is transformed. The thermostat, fireplace, and windows in this metaphor each represent processes that interact over vastly different timescales, but the metaphor helps keep the big picture in mind. At this point in our narrative, we stand at a crossroads. If for millions of years the house remains cold, the occupants adapt in ingenious ways. They huddle by the fireplace. They move into hidden rooms. Then the fireplace is stoked over and over, volcanic CO2, until finally the house warms so rapidly it feels almost oven-like. The occupants spill back into the rooms they had left, and the house is transformed. The thermostat, fireplace, and windows in this metaphor each represent processes that interact over vastly different timescales, but the metaphor helps keep the big picture in mind. At this point in our narrative, we stand at a crossroads. The physics and chemistry give plausible pathways into and out of a global or near-global glaciation,
Model worlds show how feedbacks can drive extremes and how volcanic CO2 might provide the escape route. But the truth of the matter ultimately depends on the sedimentary and geochemical record, on what the Earth left in its own archive. The rocks speak in fragments, in dropstones and striations, in isotope excursions and cap carbonates, in layers of banded iron formations that hint at a changing redox state of the oceans. Interpreting those fragments is where the debate sharpens. Some geologists read them as testimony to an all-embracing snowball. Others read them as evidence of severe but regionally variable glaciation, with life clinging to shallow, open tropical seas. So the next step in our story, and the point where the detective work intensifies, is to look carefully at those geological clues. How global were the glacial deposits? Do isotopic shifts record a simple story of CO2 collapse and rise, or do they reflect more complex local processes? How do cap carbonates form so consistently above glacial tills in many separate locations? And critically, what is the physical plausibility of survival strategies for life under different ice regimes? We will dive into these questions, one geological fingerprint at a time, and assess how each line of evidence supports or challenges the competing hypotheses. We will weigh the capacity of microbial refugia against the requirements of multicellular organisms, and we will ask what the patchy, beautiful, maddening record in stone allows us to infer about the rhythm of extinction and renewal. If you've ever wanted to watch a planetary mystery unfold, patiently, with all the argument and caution that the subject deserves, keep watching. In the next chapter, we will follow the clues in the rocks themselves, tropical dropstones and scratched bedrock, cap carbonates and isotopic anomalies. We'll look at places such as Namibia, South Australia, and parts of Canada, where the story is written in layers. We'll also interrogate the models that simulate frozen worlds and test their assumptions, because the devil and the delight of Snowball Earth lies in the interplay between empirical evidence and the mathematical worlds we use to explore possibility.
If this journey through deep time has sparked your curiosity, subscribe for the next chapter. We'll step closer to the stones and ask, one by one, what they really tell us about the most dramatic cold snap our planet may have known. We step then into the stones. Lean in, if you like. The clues are patient, and they do not shout. They whisper in layers and grain sizes, in scratched rock surfaces, and in chemical ratios that a mineral remembers long after seas have moved on. What really happened during Snowball Earth begins to resolve when we track those whispers across continents that today sit oceans apart. Start with the most cinematic evidence, glacial deposits found in ancient rocks that were laid down near the equator. These are not simply beds of gravel. In places like Namibia, South Australia, and parts of what is now Canada, geologists have mapped sequences where glacial tills, unstructured mixtures of rock fragments left by ice, sit directly beneath distinctive carbonate layers. Within the tills themselves, or in the fine sediments that surround them, we find dropstones, solitary cobbles that seem to have fallen from floating ice into otherwise quiet mud. There are also bedrock grooves, striations, where moving ice gouged the landscape. The striking thing is not just the presence of these features, but their paleolatitude. Magnetic signatures locked in the rocks show that many of these deposits were formed at latitudes that today correspond to the tropics. That magnetic fingerprint is a technical treasure because it lets us reconstruct roughly where a particular rock sat on the globe when it formed. Finding glacial deposits at tropical paleolatitudes is not something easily dismissed. It forces the question: either the climate was dramatically different, or our mapping and dating are wildly wrong. Most researchers accept the dating and the paleomagnetism, which makes the tropical glaciation problem real and urgent. Yet a headline such as "Global Ice Sheet" compresses complexities. Some glacial deposits are thick and show clear signs of ice movement, others are patchier and may record extensive seasonally mobile sea ice rather than kilometre-thick continental ice sheets. In many local sequences, the glacial units alternate with other sediment types, as if the world went on, then off, and on again. These variations are one reason why the snowball idea has a strong rival, the slushball hypothesis. In the slushball view, sea ice and glacial activity extended far from the poles, but did not necessarily weld the entire ocean into a single immobile shell. Instead, the tropics may have retained corridors of thinner ice, or even open water, allowing for ocean circulation and some degree of surface exchange. If the tropics remained open, dropstones at low latitudes could still form. Icebergs carving from ice sheets at higher latitudes could drift into lower latitudes before melting, dropping their cargo.
Conversely, if the whole ocean froze solid, how would icebergs form at all? The answer offered by the most complete Snowball models is that ice sheets could extend onto the continental shelves and carve blocks into marginal seas that would be trapped and incorporated into the sea ice package. Either way, the physical plausibility of the dropstones is not the only issue. Their global distribution, similar glacial units appearing on multiple continents, suggests a climatic signal of great scope. Above many of these glacial deposits sit cap carbonates, thick, often finely laminated carbonate layers that rarely appear in non-glacial sequences. They are remarkable in two senses. First, they sit immediately on top of the glacial rocks, as if the climate flipped almost overnight and carbonates began to rain out across newly exposed shelves. Second, their chemistry and textures differ from the usual marine limestones we expect. They often show features consistent with rapid deposition, including centimeter to meter thick beds and a range of unusual isotopic signatures. Geochemists and sedimentologists read these layers as signs of a swift change in ocean chemistry at the close of a glacial episode. To say a little more about what cap carbonates mean without letting the chemistry overwhelm the story, carbonate minerals like calcite and aragonite form when seawater is saturated in dissolved carbonate ions. The saturation state depends on pH, temperature, and the balance of dissolved ions, the ocean's chemical recipe. If, after a glacial interval, a lot of CO2 is suddenly present and weathering resumes energetically, the ocean's alkalinity and carbonate chemistry can change in ways that favor rapid carbonate precipitation. One simple way to picture this is to think of the ocean becoming briefly so rich in the ingredients for carbonate minerals that they precipitate out across broad continental shelves, leaving a distinctive cap on older sediments. The exact pathways are debated. Different researchers emphasize the roles of alkalinity from intense continental weathering, CO2 stripping from the atmosphere during warming, or changes in magnesium-calcium ratios, but the upshot remains: cap carbonates are a strong marker of a rapid post-glacial chemical shift. Banded iron formations, or BIFs, also make an appearance in the narrative, and they bring a different kind of evidence. BIFs are layered iron-rich rocks that dominated parts of the early Earth's record billions of years ago, when free oxygen was scarce. Their relative rarity after the early Archean is why the reappearance of iron precipitation in certain Neoproterozoic basins is noteworthy. If oceans were largely isolated from the atmosphere beneath thick ice, hydrothermal activity would still release iron into deep waters. That iron could persist in solution under anoxic conditions until a change, mixing, oxygenation, or a chemical shift triggered precipitation.
Thus, BIFs in the late Proterozoic can be read as a fingerprint of unusual redox structure in the ocean, consistent with strong isolation and dramatic chemical change. Isotopes are the forensic chemistry of geology. Carbon isotopes in particular are useful because the ratio of heavy to light carbon, often reported as delta 13C, responds to the balance between organic carbon burial, volcanic inputs, and weathering. During the intervals tied to extreme glaciations, the delta 13C record shows large swings, sometimes dramatic negative excursions, indicating a perturbed global carbon cycle. The meaning of any single isotopic shift is complex. Local diagenesis, fluid flow, and later alteration can overprint primary signals. But when consistent excursions align with glacial units in widely separated places, they form part of a persuasive pattern. The global carbon system was thrown into disequilibrium. So the rocks offer a chorus of signals: dropstones, striations, cap carbonates, BIFs, and isotope excursions that collectively argue for planetary-scale climate perturbations. Yet reading this chorus into a single simple narrative requires caution. Local tectonics can mimic glacial deposits, sediment transport pathways can create confusing facies, and isotopic signals can be amplified or damped by local conditions. That is why context matters. The best interpretations tie sedimentary observations to paleomagnetism, stratigraphic correlation, and multiple chemical proxies. Where the signals line up across continents, the case for large-scale glaciation strengthens. Where they do not, uncertainty grows. Let us assume for a moment that the world did tip into a state of extreme glaciation. How thin or thick would the ice have been, and what did that mean for life? Here, the contrast between snowball and slushball scenarios becomes biologically potent. In a hard snowball, kilometers of ice could cap the oceans, nearly sealing the surface from the atmosphere. Light would be blocked, photosynthesis at the seafloor would be widely suppressed. But life persists in other ways. Hydrothermal vents, driven by the ocean crust's heat and chemistry, would continue to supply warmth and reduced chemicals. Chemosynthetic bacteria and archaea could build local ecosystems independent of sunlight. Deep-sea microbial mats and vent fauna could thrive in these oases. Another refuge would be the sub-ice photic zones, if any existed. This may sound contradictory. How can light reach life beneath ice? The answer depends on ice thickness and clarity. Thin, clear ice or areas of seasonally thin ice can admit enough light for photosynthesis to occur beneath the ice surface,
particularly in shallow continental shelf regions. Modern polar seas with perennial sea ice host photosynthetic communities beneath the ice or within thin, slushy layers. If similar habitats existed in low latitudes, they could have supported photosynthetic microbes during glacial episodes.
Polynyas, persistent openings in sea ice created by wind and ocean currents, could also have provided small but biologically meaningful patches of open water. Shallow subsurface brines, protected coastal embayments warmed by geothermal input, and inland hot springs on continents might all have served as refugia. Microbial mats and stromatolites are notoriously tough. They can survive variations in light, salinity, and temperature that would be lethal to many multicellular organisms. The important point is that the fossil record suggests life did not simply go extinct wholesale. Microbial ecosystems endured, adapted, and, after the thaw, exploited the new opportunities. What about animals? The deep time record is sparse, and multicellular life was in its infancy. Claims that complex animals survived full global freeze-ups are hazardous. The safest evidence-based conclusion is that most multicellular lineages diversified after these glaciations, making use of newly available ecological niches. The post-glacial world offered nutrients and oxygen pulses that could favor evolving complexity, but whether Snowball Earth was the cause, a trigger, or an accelerating factor remains under discussion. If volcanoes were the planet's slow, relentless heater during the cold interval, then their role in the escape becomes central. With weathering curtailed by ice cover, volcanic CO2 would have been removed from the atmosphere more slowly than it was emitted. Over millions of years, CO2 could accumulate to levels far above pre-freeze concentrations in model runs. Once greenhouse forcing tipped the balance, melting would become rapid. Sea ice would retreat, albedo would fall, and a warming cascade could ensue. The pace of the thaw in many models is surprisingly swift in geological terms, thousands to tens of thousands of years of rapid deglaciation accompanied by powerful meltwater flows and sediment reworking. What would an abrupt deglaciation do to ocean chemistry? Imagine continents that had been frozen for long periods suddenly releasing torrents of meltwater laden with finely ground mineral particles. Those particles provide nutrients, iron, phosphorus, and silicon that fertilize microbial life. The result could be massive phytoplankton blooms, drawing down CO2 in some cases, but also producing oxygen through photosynthetic activity. Yet the chemistry is messy. Oxygenation can be local and episodic. Massive decay of organic matter following blooms can consume oxygen and create anoxic ents in parts of the ocean. The record contains evidence for pulses of oxygenation after glacial intervals, and these are thought by some researchers to be important in setting the stage for later complex life. Again, the language of causality is cautious. The correlations are striking and plausible, but the chain of events is complex and mediated by many variables. Cap carbonates in this post-glacial picture form as oceans readjust chemically.
Rapid input of carbonate ions, changes in alkalinity, and shifts in pH and temperature can generate conditions where carbonate minerals precipitate extensively. The result is a layer that records a world moving quickly from a chemically isolated, perhaps CO2-rich and cold ocean to a more dynamic, well-mixed temperate sea. These cap layers are, in their own way, the geological exclamation mark at the end of the freezing episode. After the dust, or rather the mud, had settled, erosion did not politely stop. Huge volumes of previously frozen sediments could be mobilized, rivers cut deep into soft beds, and continental shelves were scoured and then repopulated with new sediments. In geological terms, this is a time of turnover. Old landscapes are reworked, new chemical conditions emerge, and the availability of nutrients and oxygen may shift in ways favorable to evolutionary experimentation. The Ediacaran fossil assemblages, enigmatic, often soft-bodied organisms that appear in the wake of the Neoproterozoic glaciations, arrive in this transformed world. Whether the glaciations were the principal cause of their appearance or one of several contributing factors remains debated, but the temporal association is compelling. Now we arrive at the sharpened end of the debate. Snowball proponents emphasize the global footprint of glacial deposits and the geochemical anomalies that suggest severe isolation. They point to cap carbonates as swift planet-scale responses to a rapid and dramatic climate reversal. Slushball proponents instead note the physical difficulties of sustaining a fully frozen ocean, especially given the energy transported by currents, and argue that refugia and open equatorial waters solve the biological survival problem more straightforwardly.
Both camps lean on models that, depending on their assumptions, ice albedo properties, cloud feedbacks, ocean heat transport, produce different outcomes. Some key uncertainties center on ice thickness and the degree of ocean atmosphere isolation. If sea ice were thin at the equator, exchange of heat, gases, and nutrients could continue at levels that might prevent full chemical isolation, and life could persist more widely. If ice were meters thick, life would be squeezed into refugia, and ocean chemistry would decouple more strongly from the atmosphere. Observationally, the presence of dropstones and glacial facies at low paleolatitudes favors broad icing, but it does not settle the thickness question. Another technical difficulty is how quickly volcanic CO2 could build up and what concentrations would be necessary to overwhelm the albedo feedback. Different modeling groups produce different CO2 thresholds because they treat cloud feedbacks, sea ice dynamics, and atmospheric composition in distinct ways. Some models suggest extremely high CO2 concentrations might be required if albedo remained very high. Others allow more moderate values when different feedbacks are included.
Numerical claims circulating in discussions, such as very large multiples of pre-industrial CO2, should be treated as model outputs, not as immutable facts, unless supported by independent proxies. The central truth is qualitative. Prolonged suppression of weathering allows volcanic inputs to accumulate, and eventually greenhouse forcing can reverse the freeze. The exact numbers, however, demand humility. Then there is the question of how many such events occurred. The Neoproterozoic contains evidence for at least 2 major glaciations, commonly labelled by geologists, and some stratigraphic sequences hint at multiple pulses within a single event. The length of individual glaciations, their temporal spacing, and their drivers are active topics of research. Each proposed event adds complexity to the narrative. Repeated freezes and thaws could exert a different evolutionary pressure than a single solitary catastrophe. Throughout this debate, new techniques keep sharpening our picture. High-precision paleomagnetism, more detailed isotope work, improved stratigraphic correlation, and ever more sophisticated climate models all chip away at uncertainty. But some questions may always retain a residue of ambiguity, because we are reading processes that operated over millions of years from a partial and altered archive. That is not failure, it is the nature of deep time science. We form the best possible stories from the available evidence and refine them as new clues arrive. What then do these ancient events teach us beyond the realm of academic curiosity? 2 broad lessons are worth keeping. First, planetary climate is governed by feedbacks. The ice albedo feedback is a striking example. A small perturbation, amplified by reflectivity changes, can cascade into a phase transition. In our modern world, different feedbacks operate: permafrost thaw, ocean heat uptake, cloud effects, but the lesson holds. Feedbacks can push systems into states that are not intuitively obvious from the starting point. The technical details differ, but the conceptual point is universal. A planet's climate is not just the sum of its parts. It is an interacting system with thresholds and tipping points. Second, Snowball Earth reminds us of the resilience and adaptability of life. Microbial ecosystems are ancient and tenacious. They find ways to persist in conditions we might assume inhospitable. In planetary terms, that resilience widens the range of environments considered habitable. For astrobiology, the implications are alluring. Icy moons with subsurface oceans, Europa or Enceladus, could host chemosynthetic ecosystems in much the same way vents supported life beneath global ice on early Earth. Exoplanets with dimmer stars or with different continental arrangements might experience similar climatic extremes. Snowball Earth, in other words, is a template for thinking about habitability in a broad, comparative sense. And there is a human angle, though not a moral one. These ancient episodes remind us that the Earth has swung between very different states in its past. Our present climate sits within a relatively narrow window compared with the extremes recorded in deep time. That perspective is not a lesson in doom, it is an invitation to humility. The past does not prescribe our future, but it does tell us that the planetary system can reorganize under persistent forcings. As we draw this long chapter to a close, reflect on the image we began with: a pale, spinning globe, the surface a patchwork of ice and sea, the sun a little dimmer at a distance of deep time. The most defensible answer to what really happened during Snowball Earth is not a single sentence, but a layered statement. The geological record indicates episodes of extreme glaciation, possibly reaching low latitudes, punctuated by rapid deglaciations recorded in cap carbonates and chemical excursions.
The mechanisms behind the freeze-thaw cycles involve a confluence of tectonics, chemical weathering, solar luminosity, and feedbacks such as ice albedo, with volcanic CO2 playing a central role in the escape. Life persisted, largely microbial, in refugia ranging from hydrothermal vents to thin ice photic niches. The aftermath reshaped ocean chemistry and sedimentation, and likely influenced the conditions under which more complex life later diversified. Yet the precise details, how complete the freeze was, how thick the ice, how many episodes there were, and the exact causal chains linking glaciation to biological innovation, remain areas of active research and spirited debate. If that last sentence sounded cautious, it should. Deep time science rewards careful claims, but caution does not mean blandness. The dramatic alternation between ice and warmth, stasis and sudden change, is one of the most evocative episodes in Earth's biography. It is a story that knits together continents, chemistry, climate, and life in a way that both humbles and delights. So what really happened during Snowball Earth? The rocks tell us that something extraordinary occurred. The planet underwent episodes of far colder climate that we experience now, with wide-ranging consequences for oceans, atmosphere, and life. The best interpretations involve a web of interacting causes and feedbacks, rather than a single villain. Life found niches and survived, then flourished again in the chemical aftermath. The tale remains open, amended as new fieldwork, geochemistry, and models refine the picture. In that open-endedness resides the delight of geology, a slow, patient conversation with a planet that keeps revealing new chapters. If you enjoyed this long, sleepy journey through deep time, subscribe for the next chapter. We will explore one of those chapters in more detail, a field trip to the rocks of Namibia and South Australia, where you can almost feel the scoured surfaces and the weight of ancient ice.
Until then, rest easy knowing that Earth's history is stranger and more generous than any single explanation, and that the planet, in its slow, grand cadence, still has many stories left to tell. Good night.